All right, Chem 11, we are back. Our next lecture is the third lecture in the series of lectures dealing with naming chemical compounds. All right, like I said before, names and formulas of chemical compounds is the number one most important thing you got to know in Chemistry 11 or Chem 12 or in University Chem, whatever. Any level of chemistry, names and formulas is the number one skill you got to have. If I give you a name, you got to be able to determine the formula. Or if you see a formula, you got to be able to figure out what the name of it is. All right? So, today, we are going to figure out why you so salty. No, actually what we're going to be doing is hydrated salts and acid salts. All right? As usual, our lecture notes from the D2L page for the course are up here on the iPad in the top of the screen. And then, of course, we'll be adding stuff here to further our understanding. All right, so the first ones we're going to do, obviously, are the hydrated salts. So let's talk about what a hydrated salt is. A hydrated salt is simply an ionic compound. All salts are, right? Positive ion, negative ion, right? Sodium chloride. Sodium's positive, chlorine's negative, right? When it forms ions. So, in a hydrated salt, you still have the salt component, the ionic compound, but each molecule of the salt has a specific number of water molecules locked in with it. All right? So one salt might have, for every salt molecule, 5 waters locked into it. So every molecule of salt, there's 5 waters stuck to it. Another one, every molecule of salt might have 3 water molecules associated with it. All right? So here's kind of what a hydrated salt is. I'm going to use the example of copper 2 sulfate pentahydrate. Now, copper 2 sulfate pentahydrate in its hydrated form, which means when the water is there, is a really nice blue crystal. Like it's a really nice looking compound, right? And what I can do to that hydrated salt, which has the salt and the water molecules in there, is I can heat it up, right? We've got the delta sign here. That means I can heat that hydrated salt up, and what will happen is the water will escape and it will evaporate into the air. It'll become water vapor and leave the salt molecule. When that happens, we're left with the anhydrous form of the salt. And for copper 2 sulfate pentahydrate, that's a whitish, flaky material, right? So here we can see the delta sign. We added some heat. We heated up our hydrated salt, and we got the anhydrous form of the salt. Anhydrous meaning not hydrated, right? Like in ecology, you had biotic factors and abiotic. The A in front meant not biotic. Or in biology, you have aerobic respiration and anaerobic. Aerobic is with oxygen, anaerobic means without. This is without water because we heated it up and the water evaporated into the air. All right? Now, if we take this and add the water back into it, take an eyedropper and add some drops of water to it, it will reabsorb the water molecules and go back to the hydrated form of the salt. All right? So, when we name these salts, what we're going to do is this, and I'll put the 2 examples here. These are the same examples at the bottom of our screen. I'm going to rewrite them out here so we can break them down and figure out what we got to do. Now, the first thing you'll notice is that each of these formulas is basically cut in half. I've got a salt, and then I've got the water and this little dot in the middle. There's my salt, there's that dot separating them, and there's the water. This is how we're going to name them. And the reason that dot is there is because the water isn't locked in there where it can never escape. As we just saw when we heat it up, the water is capable of separating and going away from the salt, leaving the anhydrous form. So to kind of show that, yeah, they're together, but they're easily separated, we just have this dot here, all right? Now, we'll do this one first. So this is going to be magnesium bromide. I named the salt first. All right, magnesium bromide. That's a binary ionic compound. I know how to do that. The second part, 7 waters. Now I have to make sure that in that name I refer to the fact that there is 7 waters. So I'm going to use the same prefix as you use in covalent compounds: mono, di, tri, tetra, penta, hexa, hepta, octa, nona, deca. You learned these in grade 10 when we did covalent compounds. They're the prefixes. So magnesium bromide, heptahydrate. Magnesium bromide heptahydrate. All right? Now this one over here, this is going to be copper. Now I know copper's shifty, right? It's one of my shifty multivalent metals. So I got to put a Roman numeral there. SO4, that's sulfate from Nick the Camel, right? SO4 is sulfate. So that's my salt. Copper, something sulfate. I'll figure that out in a moment. 5 waters. 5 is penta, so this is pentahydrate. All right, now this copper, CuSO4, right? What I'm going to do is I'm going to go with what I know. I'm going to use that zero sum rule we talked about. I got to figure out the charge on the copper. What do I know? I know I got 1 copper and I have 1 sulfate cluster. Remember, this 4 is part of that cluster. So I have 1 sulfate thing here, 1 sulfate group. The charge on a sulfate is 2 minus. 1 times 2 minus is 2 minus. If this side is 2 minus, it means this side has to be 2 plus. 1 times what gives me the 2? It's going to be copper 2 sulfate pentahydrate. All right, easy enough? All right, so copper 2 sulfate pentahydrate, magnesium bromide heptahydrate. All right? And if it's online, it must be true. Good old Abraham Lincoln taught us that. All right. Now the acid salts. I'll bring all this up and we'll talk about it. In class, I would expand that out. But here's basically what an acid salt is. I'm going to use sulfuric acid as my example. Sulfuric acid. Now this is not an acid salt. That's an acid, right? If I take sulfuric acid and I put it in with a strong base, this is what happens. Or if I put it in with water, this is quite often what will happen. There's my acid. I drop it into some water or a strong base. The acid dissociates or ionizes, which means it falls apart into its component ions. So if I look at it, there's 2 hydrogen ions and 1 sulfate ion. And it will all fall apart in a strong base or in something like water. So I put this in, bloop, and it falls apart, right? 2 H ions and an SO4 ion, right? Now we know the hydrogen ions are protons. So we get 2 protons and a sulfate, right? Polyatomic ion. Well, that's fine and dandy. Acid salts are formed when we drop that same acid into a weak base this time. So not a strong base, a weak base. And that acid doesn't fully dissociate, right? If we look what happened before, it entirely comes apart. The 2 H's and the SO4, I get 3 ions. But look what happens here. In this instance, only 1 of the hydrogens comes off, right? The other one stays with the sulfate. And what this forms is the bisulfate ion. Bi means there's a hydrogen on it. Or you can call it the hydrogen sulfate ion. All right? So what that means is you end up with this HSO4. When I put a strong acid in a weak base, it doesn't fully come apart, and I end up with this. All right? Now if we look at this, again, sulfate had a 2 minus charge, but this thing only has a 1 minus charge. What's the difference? Well, if I look at it, and I'll write it over here, sulfate is 2 minus, but now I've got this hydrogen with it, and hydrogen is a 1 plus. 1 plus and 2 minus together is only 1 minus. All right? So, the charge on the bisulfate ion is 1 less than it is on the sulfate ion. Bisulfate, its charge is 1 less than sulfate, which would be 2 minus. All right? Now, this bisulfate ion, it's capable now of going out and combining with something positive, like a sodium ion. And we'll end up with sodium bisulfate. Sodium bisulfate. Right? Sodium bisulfate. I name the metal sodium. Bi means there's a hydrogen, and SO4 is sulfate. Sodium bisulfate. Or you can do the longer way. Name that metal sodium hydrogen sulfate. Now we know chemists are lazy. I kind of prefer this way up here using the bi, but if you write this, you're fine as well. All right? So we've got some examples here. One of them I've already done, but we'll do the other two. All right? So CaHSO3, 2. I know that this is calcium. I don't change the name of the metal. I don't change the name of the metal. It stays as calcium. And HSO3. The H is bi, and now SO3. Sulfate is SO4, SO3 is sulfite. We covered that in the previous lecture. So this is calcium bisulfate, or I could say calcium hydrogen sulfate. Sorry. So calcium bisulfite or calcium hydrogen sulfite. All right? Be careful between your ites and eights. The other one, the third one here, magnesium HCO3, 2. This is going to be magnesium. This is carbonate, and with the H, it's bicarbonate. Right, I use camel. Nick the camel helps me with this. Magnesium bicarbonate, or I can call it magnesium hydrogen carbonate. Either one is entirely acceptable. All right? And as we see, if it's online, it must be true. And this just explains that you can use hydrogen instead of bi, just like we did here. Sodium bisulfate or sodium hydrogen sulfate. Calcium bisulfite or calcium hydrogen sulfite. Magnesium bicarbonate or magnesium hydrogen carbonate. It's up to you. Whatever way you want to do it is fine. I will accept either one. All right? Anyway, that's it. That's all I got for today. Acids we're going to save for another lecture. And so good luck sleeping if you're worried about acids today. We're not going to learn them. That's all I got for today. If you have any questions, comments, or concerns, throw them in the comment section below this YouTube video, or reach out to me using Edsby if you're in my class, or heaven forbid, raise your hand if you're actually in person in class. Ask questions. You can't just sit there and not know. Anyway, I hope everything's crystal clear. I'll talk to you soon. Take care. Bye-bye.